Hey Zed Physics, do you mind just quickly finding the range of a projectile for me? Oh, of course! In fact, I was just working on that. What a coincidence, it's almost as if I planned it or something. These are our horizontal and vertical speeds. Then to find the range, multiply the horizontal speed, which is constant because there's no forces acting in that direction. Whoa. What are you doing? Okay, this will be true if there was no air resistance, but realistically, how many times have you thrown a ball in a vacuum? Well, that sounds kind of fun, but I don't really have a vacuum chamber, so... Exactly! So why don't you do it properly, taking into account air resistance? Actually include air resistance in the calculation? Do you have any idea how complicated this will be? Just this one extra term? Physicists. This is an entirely different problem with air resistance added. The equation of motion is now mass times acceleration. The net force is the sum of all forces. We are going to have a resistive force which is proportional to the speed. Please know that we're just assuming that it's proportional to v. In reality, air resistance is even more complicated and you will often see it being proportional to v squared. We also have the weight as part of the equation, and what we need to do is to find the range if the projectile starts at the origin with an initial velocity u in the x direction and w in the y direction. The first thing that I'm going to do is just divide all sides by m, so I'm going to get that a is equal to minus lambda over m times v take away g. Now because I'm going to be writing out this term quite a lot, it's very useful to give it a separate letter so you don't have to keep on writing minus lambda over m. So I'm going to say that this here is equal to minus gamma multiplied by the speed, which is the first derivative with respect to time of the displacement. Always useful to write down acceleration speed in terms of derivatives. So the acceleration will be the second derivative, and let's not forget the gravitational term. And now we have an interesting differential equation to solve. The differential equation will actually be different in the x direction and in the y direction. In the x direction, we don't have gravity which is acting because that's purely vertical. So we can say that the second derivative of the x position will be given by minus gamma times the first derivative. In other words, we can also rewrite this as x double dot plus gamma x is equal to 0. And now let's integrate both sides of this equation with respect to time. So I'm going to integrate this, I'm going to integrate this with respect to time. And what I'm going to get is the first derivative of x plus gamma times x will be equal to some constant of integration. And in order to solve this, we need to employ an amazing technique in solving differential equations, and that is multiplying by integrating factors. Some of you guys will be familiar with this technique, but some of you will not be, and it's really fascinating to see how this works. So look at this, x dot plus x. This kind of reminds me of the product rule. So if I was to differentiate a product, something like u times v, well, this here will be given by the derivative of u times v plus v dot times u. And look at this, this is kind of similar to what we have here. I have a derivative plus something multiplying the function itself, kind of like how I have u dot here and then u here. In its current form though, we have a 1 and then a gamma here, so this is not quite in the same form. However, we can force it to be, we can multiply it by a function that we're going to define such as that it fits this bill. Let me show you. So I'm going to say that this function is just called f. So I'm multiplying by fx dot plus f gamma x, and this here will be given by f multiplied by that constant. Well, if we define define the function f to fit in terms of the product rule, then this here, f multiplied by gamma, will be exactly the same as the time derivative. So just as an aside here, we can say that f times gamma will be given by the time derivative of f. In other words, gamma will be given by f dot divided by f. And I can yet again integrate both sides, and what I'm going to get is that gamma t will be given by the integral of f dot over f. This is just ln of the absolute value of f. How do I know that this is the correct integral? Well, ln of f, if I was to differentiate that, I would get 1 over f, but then I would need to multiply by the time derivative of this function with the chain rule giving us f dot over f. There's also some constant of integration, but we're going to absorb that later on into the original expression. And in order to get the function f, all we need to do is take the exponential of both sides. So we're going to get e to the gamma t is equal to e raised to that. Remember, those guys here essentially cancel out. So what we're left with is that our function f is indeed e raised to the gamma t. And here is how this beautiful technique works here. So f is just e to the gamma t multiplied by x dot plus e to the gamma t times x, and this here is equal to e to the gamma t multiplied by that constant. Because of the product rule, we've defined the functions such as the whole of the left-hand side of the equation is just equal to the time derivative of the product of those functions. So what we get is d by dt of u times v, which is f times x, and f is just gamma multiplied by t, then multiplied by x, and this here will be given by e to the gamma t multiplied by that constant c. We're once again going to integrate in this problem, so I'm going to take the integral of this side. I'm going to add a little dt here. I'm going to take the integral of this side. I'm going to add a little dt on this side here as well. So the integral of the derivative, that's just whatever the function on the inside is, i.e. e gamma t multiplied by x. And this here will be given by the integral of this function, which is just going to be e to the gamma t divided by gamma times c, and then plus yet another constant of integration for this operation. I'm just going to call this one c2. Okay, we're nearly there. Now I can get rid of some of these factors. So I'm going to say that x is going to equal to that, e to the gamma t. Let's see, what have we got left? We have c over gamma plus c2 multiplied by e to the minus gamma t. All we need to do is just figure out what those two constants are, and then we have an equation for x. And this is where we're going to be using the boundary conditions of our problem. We know that the initial speed is u, and we know that the initial starting position is 0. So we know that x dot at a time t is equal to 0 will be given by the expression u. So let's just differentiate this expression and let's see what we're going to get. So x dot will be given by this thing here will disappear. Then we're going to get a factor of minus gamma c2 e to the minus gamma t. Okay, well, at t is equal to 0, this exponential here is just equal to 1, and we know that x dot at t is equal to 0 is just equal to u. So we can say that C2 will be given by minus u divided by gamma. Time for the second boundary condition to figure out what C is. So at t is equal to 0, x should be equal to 0, assuming that we start at the origin. So let's see, what would that give us? X at t is equal to 0 is just going to give me c over gamma plus c2, which was just minus u over gamma. So this here means that 0 is equal to c over gamma minus u over gamma. So this means that c will pretty much have to be equal to u. And here we finally have an expression for the x-coordinate, having substituted both of those constants in. And now it's time for the y direction, which is even more complicated. So the differential equation is that the acceleration of the y component will be given by minus gamma times y dot, take away the gravitational component. The first thing I'm going to do is just bring this over on the other side. So what we get is y double dot plus gamma y dot is going to equal to minus g. Now, similarly to the previous example, I'm going to integrate both sides with respect to time. So let's see what we get. This here will turn into y dot plus gamma multiplied by y, and this here will be equal to minus gt plus some sort of a constant that we're going to find in a little bit. Now, this is incredibly similar to the example that we had before, and it will require the same constant factor of integration, which, if you remember, our function f, so I'll just write this in a different color, was just e to the gamma t. So what I'm going to do is I'm going to multiply all of this equation by that factor. And remember, we have defined f in such a way that f times gamma is in fact equal to the time derivative of f. This means that we can apply the product rule directly on the left hand side, and what we're going to get on the left hand side, that this here is actually the time derivative of f multiplied by y, which will be given by minus gtf plus c times f. Find f. I follow exactly the same steps as the previous part of the equation. We're going to get exactly the same answer, that it's e to the gamma t. So I can directly put this into this part of the equation. See, magic. And now let's integrate yet again both sides of this equation. So let's choose the different color for the integral sign. We're going to have the integral of this side with respect to t, and then the integral of this whole thing, let's add in some brackets, with respect to t. Okay, let's tackle yet another integral. So on the left hand side, we have the integral of the derivative, which is just going to give me e to the gamma t multiplied by y. Now on the left hand side, we have kind of a tricky integral. So first of all, we have the integral of minus g times t e to the gamma t dt plus the integral of c e to the gamma t dt. Okay, so much integration. I'm starting to regret agreeing to do this. But looking at this, probably the easiest way, correct me if I'm wrong, would be to use integration by parts. So I'm going to have to deal with this integral separately. The rule that I'm going to use is that the integral of u dv will be equal to uv take away v du, if I remember correctly. Whenever I use this technique, I normally just identify what is u, what is dv, and what is du, so I'm going to do exactly that. And because I'm applying this rule to this integral, let's see, so let's take dv to be e to the gamma t. Now this would mean that v will be the integral of that, which is going to be e to the gamma t divided by gamma. Okay, now we're going to take our u to be just t, which means that our du will just be 1, well, dt. Okay, we're ready to apply this rule. So what do we get? The integral of u dv, which is t e to the gamma t, will be given by u times v. So that's going to be t multiplied by e to the gamma t divided by gamma. And then we're going to take away the integral of v, which is e to the gamma t divided by gamma, multiplied by u, which is just dt. Okay, we're kind of getting there. What do we have? T e to the gamma t divided by gamma, take away e to the gamma t divided by gamma squared. We get yet another factor, and I will try not to forget my constant of integration. Let's see, shall we just call it C2? I could even factor out e to the gamma t, and what do I get? T over gamma minus 1 over gamma squared plus C2. I think that's right. So what I'm going to do is I'm going to bring it over on this side. So what I get is e to the gamma t. Ooh, my gamma kind of looks like an alpha here. Sorry about that. Okay, e raised to the gamma t multiplied by y will be given by minus g times e to the gamma t multiplied by t over gamma minus 1 over gamma squared plus this constant of integration, and then plus c over gamma, which was the other constant of integration, times e to the gamma t. I'm also getting another constant of integration from this one, but I will just be absorbing it directly into this one here. Okay, I think it's time to do some cancellations, about time to actually simplify this expression a little bit. So let's see what we can do. First of all, I'm going to get rid of this e to the gamma t here, which means I'm going to have e to the gamma t here, and then I can get rid of this one as well. So what I'm left with is that y is equal to minus g t over gamma, take away 1 over gamma squared, plus c2, and then e to the, I'm going to say, minus gamma t, and then this c here is a constant, then I'm dividing it by another constant, so I'm just going to absorb this into the constant. I'm just going to call this thing c1. This is just for ease of writing, nothing more. And there we have it. This here is a general solution for the y coordinate. Now I can use the boundary conditions to figure out my constants of integration yet again. So we know that the starting position is 0, 0, and we know that the initial velocity in the y direction is just w. I will first use this initial boundary condition about the speed. So I'm going to say that y dot is equal to, now what do we have? This term here, minus gt over gamma. Whenever we differentiate that, what we'll have left, which is going to be minus g over gamma. This term here is a constant that's going to disappear. Plus, we're going to have a c2 term, e to the minus gamma t. When that thing here is differentiated, we also get a factor of minus gamma, and then this constant here will conveniently disappear. Okay, now let's evaluate this at t is equal to 0. What this thing here will actually turn to will be the following. So y dot at t is equal to 0 is just w. So we have w will be minus g divided by gamma plus C2 times minus gamma. I'm just going to write this as minus C2 times gamma. This term here will disappear because e to the power of 0 is just 1. So, okay, that's not looking too bad so far. I can directly rearrange for C2. I'm just going to do that here. C2 gamma will be minus g over gamma, and then minus w. Let's get rid of this factor of gamma. So what we have is minus g over gamma squared, take away w, divided by gamma. And this here is the constant. So now we know what this constant is. What we need to do is figure out this constant here. Well, to figure out the other one, I just need to use the other boundary condition that my initial position is just at 0, 0. Okay, well, let's do this. So I am going to say that y at t is equal to 0. Well, this here will just be equal to 0. So what will this expression for y look like when t is equal to 0? First of all, this term here will actually disappear because t is equal to 0. This term here will be fine. Let's just start writing it down actually. So y of 0 is just 0, assuming we start at the origin. Will be given by minus g times this term here, which is going to give me a plus g over gamma squared. This is this times that, plus C2. Now this term here, e to the minus gamma t, will turn into e to the minus, or e to the 0, which is just 1. So this will just be plus C2. And then what we're going to have is plus C1. Now we already know what C2 is because this thing here is just this expression, which is minus g over gamma squared minus omega over gamma plus C1. Look at this, so convenient. This term here will cancel with this one, so what we're left with is that C1 should just be equal to w over gamma. When we place our values for the constants into the original expression, we actually finally have an expression for the y-coordinate of this projectile with air resistance added. Just look how much more complicated it is, but we're almost there. Okay, now here's my secret plan to get an equation that is independent of the time. First of all, I'm going to get the x equation that we have already, and I'm going to combine that with the equation in the y direction by eliminating time. So all we need to do is just rearrange this equation for the time. So let's do it. Okay, well, x will be u over gamma, take away u over gamma, e to the minus gamma t. Let's just rearrange for that. So minus u over gamma e to the minus gamma t. This here will just be equal to x take away u over gamma. Here means that e to the minus gamma t. This thing here will be equal to those two that have been swapped. So I'm going to have u over gamma. Then I had a factor of u over gamma here, which will essentially cancel out. So gamma over u, all of this will cancel out. Then we're going to take away a factor of x, and then that would have been multiplied by gamma divided by u. So x times gamma divided by u. Okay, now I'm going to take the natural log of both sides so I can get rid of this exponential. So that's going to go, and what I'm left with is minus gamma t will be given by the natural log of 1 take away x gamma divided by u, and all we need to do is do minus ln absolute value take away x gamma over u, divide that. Ooh, that's like the worst it's like the worst division sign I've ever drawn, and all I need to do is just divide that by gamma. Okay, and now we have the joy of taking this expression for t and then plugging it into here. Hopefully I'll do like a little time lapse when I'm actually editing this. And this right here is actually an expression for the y-coordinate with respect to time. And even though it's pretty complicated, and I know I could factorize it a little bit better, but frankly, after so much math, I'm just not going to do it. But what I'm going to do is analyze it a little bit. Now, look at this. We have a factor of ln of 1 take away this and 1 over this, but the natural log function needs to be positive. This, of course, though, means that x gamma over u can never really be equal to 1, because then this term here will turn into 0 and the whole equation will become undefined. So that means that the x-coordinate actually cannot reach a value which is greater than u over gamma. This absolutely cannot happen. If that is the case, because this here will be the dominating term in this equation, the natural log function will actually start tending towards negative y, and this right here will essentially be just a vertical drop once all of the speed in the x direction has gone, and the object will just essentially fall off vertically. Now, if you've watched this video right until the end, I have to say congratulations. This is definitely a university level problem. It was a lot of fun actually to film, and you should probably take a little rest right now because it's well deserved. However, if this was not enough physics for you, you need to have a look at a projectile motion problem, which will now feel incredibly easy, and this video is right over here. Check that one out.